Yeah, and welcome back, everyone. Hope you all have a great summer. And as you know, Toronto Air Seminar is resuming this fall semester. And for today, we are glad to have Daniel Bruder to give a talk on making soft robotics less hard towards a unified modeling, design, and a control framework. Daniel Bruder received his bachelor degree in engineering sciences from Harvard University in 2013 and a PhD in mechanical engineering from the University of Michigan in 2020. He is currently a postdoc doctoral fellow in the Harvard Micro Robotics Lab, supervised by Professor Robert Wood. He is also a recipient of the NSF Graduate Research Fellowship and the Richard and Eleanor Connor Prize for outstanding PhD research. His research interests include design, modeling, and control of robotic systems, especially soft robots. Welcome again, Dan, for your coming, and the stage is yours.
Hey, thank you so much for the introduction, and thanks for inviting me to be here today. It's great to be here with you all digitally. So yeah, to start, I think I'll start with why should we care about soft robots? So the type of robots that most people are most familiar with are these types of robots, which are rigid robots. They're made of stiff links and they have these strong and heavy motors. And these types of robots are fast, they're accurate, they're precise, and they have like large force outputs, which is exactly what we want for industrial tasks like making cars. But these same robots, if they perform the wrong behavior in the presence of humans, have the potential to cause serious injury or even death. So as you can see from this simulation with the dummy, in real industrial settings, usually we keep robots and humans physically separated so that they don't interact at all. But for robots to become more useful in our day-to-day lives, we need them to be able to safely interact with humans, because many of the tasks that we do on a day-to-day basis involve physical contact with humans. So take, for example, the task of feeding, where, again, if I have a rigid-bodied robot, it's not back drivable, and if it has the wrong behavior, it has the potential to cause injury. So if we instead build our robots out of soft materials with inherent compliance, we can build systems that, even in the event of complete failure in terms of control, still offer some sort of inherent safety in interacting with humans. And so that's one of the main benefits of soft robotics, but it really only scratches the surface, because in addition to being able to safely interact with humans, which is shown up here, they can also do things that would be really difficult to achieve with rigid-bodied robots, such as navigating through their environment through contact, by being able to absorb impacts without taking damage. They can conform their shape to grasp objects of various shapes and sizes without any sort of sophisticated control. And they can much better emulate the types of motions and morphologies that we see in natural systems like fish and snakes. So given all of these potential benefits, the overall goal of my research is to try to actualize soft robots that can safely perform real-world tasks, especially those in which safety and adaptability are just as important or more important than precision. So some examples of those types of tasks are assisting the elderly with things like feeding, bathing, getting dressed, where it's a class of tasks where you need to be gentle just as much as you need to be precise. Domestic chores, those involve interacting in unstructured human environments and interacting with humans, as well as all sorts of different objects and geometries. And then even in exploration and inspection tasks, it's really nice to have robots that are able to adapt to unstructured and unpredictable terrain. And so even in that domain, soft robots, I think, could be useful. And so the approach that I take to trying to get soft robots towards these real world tasks is modeling, design, and control. So I focus on all three, and specifically the questions that I'm trying to answer are, in design, how do we build robots that are physically capable of performing these types of tasks? In modeling, the question is, how do we describe the robot behavior in useful ways that will allow us to actually control the robots and get them to perform the tasks that we want them to perform? So that's the overall goal, and these are the subdomains within. And I try to take an integrated approach to modeling, design, and control, considering sort of all three at once. And so in my past work, one of the approaches I took was to try to develop a design-oriented, physics-based modeling approach for soft robots. So this type of design-oriented approach lets you consider a bunch of different soft robot designs before you actually physically construct them. And then it gives us a principled way to do steady state control of soft robotic systems. But as it turns out, in order to build a physics-based model, you tend to have to make a lot of simplifying assumptions. And so this modeling approach isn't useful for doing dynamical control of soft robotic systems. So I'm actually not going to talk about this physics-based approach at all today. Instead, I'm going to talk about a second approach that I developed in past work, which is a control-oriented approach that's data-driven. And so what this control-oriented approach lets us do is actually take a real soft robotic system to learn a representation of the dynamics of that soft robot as a linear representation. And then with that linear representation of the robot's dynamics, we can apply linear optimal control algorithms to control these robots beyond the previous state of the art. And so this is what I'm going to talk about today, is this Koopman-based data-driven approach for soft robots and how it enables new behaviors that we couldn't achieve before. Okay, so the first question might be, why is it a good idea to take a data-driven approach to modeling soft robots? And it turns out that soft robots are actually particularly amenable to data-driven methods for a few reasons. One, at least compared to rigid-bodied robots, it's really safe to collect data from them because, like in this video, I can command my robot under pretty much random control inputs, and I don't have to worry about it damaging itself or its surroundings. The second is that by building models from data rather than from physics, we can avoid making the type of restrictive assumptions that we typically have to make those types of models tractable. And along with that comes the ability to account for fabrication defects explicitly in our models, which tend to play a pretty large role in these handmade soft robotic systems. But I said before that I'm trying to build a control-oriented modeling approach, and not all data-driven models will actually be useful for control. So we have to take a more particular approach to this. So when I say a model is control-oriented, what do I mean? Well, in my mind, there are two things that I really want to have in a model to help me do control. The first, as with pretty much any model, is that I want it to be able to accurately predict the behavior of my real system. But the second thing I'd like in my model is for it to be linear, because if I have a linear dynamical model, that means I can apply off-the-shelf, computationally efficient linear control techniques to make the system behave the way I want it to. So if I started from the framework of I would just want my model to be linear, I could do linear regression on collected data and identify a linear model in the subspace method. And I would end up with a model that's linear. But if the underlying dynamics of that system are nonlinear, chances are my representation won't be very accurate. So another approach I could take is, okay, well, I just want to focus on accuracy. So I'm going to train a neural network to get the best, predictions for how this system will behave possible. And in that case, I'll get something that's really accurate, but I won't have a linear representation of my dynamic. So there seems to be, this trade-off between linearity and accuracy when we're trying to model nonlinear systems. And so the really cool thing about the approach that I'm about to talk about, based on the Koopman operator, is that it gives us a way to build dynamical system models that are accurate, but they still give us a linear representation of our data. And it's not a local linearization, it's actually a global linear representation of the dynamical system. So to understand the big idea behind this Koopman operator approach, I think it's actually useful to use an analogy from machine learning, specifically the task of classifying data points. So, say I have some set of data points here labeled in red and in blue, and I want to write a classification algorithm to label unlabeled data points. Well, if my points look like this, then I can draw a boundary between the two as just a line. So there's this linear boundary. And that means that I can write my classification algorithm as a simple linear program, which is really efficient, and I like it. But if my points instead are distributed like this, I can't actually separate them with a line anymore. Instead, I would need a circle or some other nonlinear boundary. And that's bad news for me, because this means that now my classification algorithm has to be a nonlinear program, which isn't quite as nice and efficient. But there is a trick that I can use. If I take my data points and I lift them into a three-dimensional space where I've defined this third dimension as a function of the other two, so x squared plus y squared, I get now my data points live on this paraboloid in 3D space, and I can separate the red and blue points by a plane, which in 3D space is a linear boundary. So by lifting my data into a higher dimensional space, I've recovered the ability to build a classification algorithm that's linear. So I increased the dimension, but I got a representation that was more efficient for what I was trying to do. And so what the Koopman operator does is it applies this same idea to dynamical systems. So if I have a nonlinear dynamical system that evolves in some state space, I can lift it into a higher dimensional space. And in that higher dimensional space, the Koopman operator is a linear operator that describes its evolution. So how does this actually work? Like, what is the definition of our Koopman operator? So to see this, let's consider an arbitrary nonlinear dynamical system, which we can describe as a continuous differential equation or with a discrete flow map. And so if I have some initial state x naught, and then I apply the flow map to it, I can build up the trajectory of this dynamical system over a bunch of points through time. And so now I introduce the Koopman operator, K. And it's defined as the linear operator that composes scalar valued functions with the discrete flow map of my dynamical system. Okay, so what does this actually look like? If I define some real valued function over my state space, and I evaluate that function at the initial state, and then I were to apply the Koopman operator to that function, what that gives me is the value of that function one time step later along the trajectory of the underlying nonlinear dynamical system. And so you can see that if we repeatedly apply this linear operation, the Koopman operator, we can build up a trajectory of the function values through time. And from that, we can actually recover the future values of the state as well. So this gives us a way to linearly compute future values of the system. And now,
then may I ask a question here?
Yeah, sure.
So this computation is not exact, right? The Koopman operator only gives you an approximation.
In practice, that is true, because the Koopman operator in principle is an infinite dimensional operator.
But in theory, it gives you the exact.
Yeah, exactly. In theory, it's giving you the exact, but that's only if, it's like in theory, it's defined this way. It's defined such that it satisfies this.
Okay.
But when we use it in practice, it's always an approximation.
Yeah, you have to do some discretization somewhere.
That's right. Yep. I'll talk about that on the next slide. And I just want to mention, so I just showed for this example of a version where there's no control inputs for simplicity. But this same idea actually extends to systems that have control inputs under some assumptions. So we assume that the control input is a constant across time steps, but it still holds. So as for so this speaks to Igor's question. So basically, you look at this and you go, well, this is magic. Like, if every nonlinear system can be linear, like why is there any issues in control today? And that's because, this isn't a magic bullet. The caveat is that even though the Koopman operator is linear, it's infinite dimensional because it's an operator that acts on functions, not finite dimensional vectors. So when we want to use this Koopman-based linearization in practice, we always have to settle for its approximation restricted to some finite dimensional subspace. So what I do in practice is I define some finite dimensional subspace by choosing a set of basis functions. And so these basis functions could be Fourier basis functions, they could be Gaussian radial basis functions, polynomials. It's user, you can choose based on your system. And so once I've defined this subspace, I can now represent functions within the subspace as a finite dimensional vector, where each component of the vector, these C's here, are just the weight associated with each of the basis functions. And then likewise, my Koopman operator, which is an operator on functions, can be represented now as a finite dimensional n by n matrix. So I can rewrite this definition from the previous slide in terms of this new matrix vector notation, where K bar is how I signify the Koopman matrix. And if we simplify this definition by canceling out C from both sides, what we get is basically this relationship, which says that if I take the transpose of this Koopman matrix and apply it to the vector of all basis functions, it'll advance that vector of basis functions forward in time one time step. So essentially, the Koopman matrix acts as a discrete flow map on a quote unquote lifted state, which is an n-dimensional state comprised of all of my basis functions evaluated at the underlying state of the system. So the question is, how do I actually identify a Koopman operator model for a real system and then use it for prediction and control? And so to show that, I'm going to walk through how we did this for this soft robotic system, which is a pneumatically controlled soft robot arm with a laser pointer on it, where the state of the system is the position of the laser pointer dot on a sheet mounted below it. So the first step in this process is to collect a bunch of data. It's a data-driven process. So we command the robot under randomized pressure inputs and measure the position of the laser dot. Then we take all of those input-output data pairs and we lift it into a higher dimensional space by evaluating each point by evaluating a set of basis functions at each of those points. And so for this example, I use a set of basis functions that consists of monomials of the components of the state up to degree 2, which for shorthand, I'm calling Z, as well as the input of the system appended to the end of that set of basis. And so now I have all my data in a higher dimensional space, and I can identify the Koopman matrix simply by doing linear regression on that lifted data. And so I do linear regression, and I find the matrix that best describes the one-step transition between consecutive lifted data points over all those data points. And so now I have this linear representation of my system, and I can either decompose it to get a linear time invariant representation of my dynamics with respect to Z, which is the lifted state, or I can actually project back down into the original state space and recover a nonlinear model, which is basically just a weighted sum of basis functions that I chose. So when we take those Koopman models, both the linear and the nonlinear version, and then compare its predictions over a 6-second horizon to the real system, where the real trajectory is shown in gray and the predictions are shown in the colors, we can see that at least for this system, the Koopman models gave better predictions over this horizon than comparable models that were trained on the non-lifted data. So if I learn a linear model without lifting the data, I get this prediction. And if I learn a nonlinear model using a neural network on the non-lifted data, I get this prediction. And so in this case, the Koopman model actually gives us better predictions than these comparable tools. Now, this isn't always going to be the case, but it shows that the Koopman operator can give us good predictions, which is, the first important thing, that our model's accurate. But the really useful part of the Koopman operator comes when we think about control. Because now we have a linear representation of our dynamics, we can now use that in a optimal control framework and really efficiently compute optimal inputs. So that's what we did. So we take the Koopman model and incorporate it into a model predictive control framework. And so for those who are unfamiliar with model predictive control, I'll go through sort of a quick overview of how it works. Basically, at every time step, we measure the current state of the system, and then we solve an optimization problem that is trying to minimize some cost function, usually a deviation from some type of desired reference trajectory, over a sequence of, in this case, lifted states and inputs. And so we make sure that those sequences are subject to the constraints that they obey the linear model dynamics of our system, and they're consistent with the initial condition, which is the current measured state. And so once we solve for, yeah, go ahead.
Sorry. One other question with regard to your formulation. You use monomials as your basis functions. Does this make your Koopman operator related somehow to the basically Taylor series expansion and for multivariate functions?
So I didn't explicit. So there is a way that you can. I didn't explicitly choose the basis functions to basically give me a Taylor series representation where you want to basically include like the third, as many derivatives of your dynamics as possible. But essentially, that is what I assume is being built through this linear regression process.
So basically, when you choose them as monomials, you end up with a Taylor series approximation.
Yeah.
Is that accurate to say?
I think that's I think it's accurate to say. I mean, to know for sure, you would need to know the dynamics of your system
Right.
and know the Taylor series, and then you could compare the weights that the Koopman operator
Yes.
gives you to what
Right.
the Taylor series is. And I couldn't say like if it necessarily is going to give you the Taylor series. I think it probably depends
Yeah.
on
Okay.
the
Makes
system
sense.
and the uniqueness of things.
Yeah. Okay.
But there are ways of, if you do know the dynamics, you know, there's explicit Koopman linearization where you choose basis functions to try to build a Taylor series. And there's some other papers that do that type of thing. Yeah. And when you do that, you can show some like there's ways of showing some kind of bounds on the accuracy of your approximation, similar to like a Taylor series, like error
Because
bound.
you can use the approximations for the Taylor series for your Koopman dynamic.
Exactly.
Okay.
But to do that, you know, you have to have at least some starting dynamics for your system. And in this case, we started with nothing. We just assumed we don't know anything about the dynamics. And, you know, chose the basis functions really just to be generic. So like, this is a generic, you know, set of basis functions. Let's see if it works. And we tried some other basis functions like with sinusoids and Gaussians, and they also, you know, gave decent predictions, but the polynomials actually worked the best for this system. So something about the underlying dynamics were amenable to using those.
Yeah, makes sense.
Yeah, thanks for the question. Okay, so MPC, we solve for an optimal sequence of inputs that will get us closest to our desired reference trajectory. And then we actually take those optimal inputs and apply it to our system for one or more consecutive time steps. And then we repeat this process over and over again. And so by repeatedly solving this problem, it lets it lets the controller, you know, correct for modeling errors and prediction errors, because it's updating, you know, it's recomputing the optimal input at each time step. So, you know, how does the Koopman operator help us here? Well, because the Koopman operator gives us this linear representation of our dynamics, that makes this optimization problem convex. So that means we have a global convergence guarantee, and we have efficient methods for solving that optimization problem. So here we have used a model predictive controller running at about 40 hertz. I think it was 40 hertz on the laser pointer system. And this lets us do arbitrary trajectory following with the laser dot. So shown here are a few examples of different trajectories that were not part of the training data set at all. So it's not like we trained it to explicitly draw a star or a circle. This is just having it doing MPC to follow these reference trajectories. So we get you know, sort of decent following, and if we compare that to the results when we use a model predictive controller built on a linear model from the unlifted data, so the linear model that wasn't lifted into the Koopman space, we see the Koopman model does much better, and in fact, it's roughly 4 times more accurate and more precise than the non-lifted MPC controller. So we were pretty excited about those results, and I wanted to see, okay, that works for this sort of simplified laser robot, but will it work for a more complicated robot that can, you know, do more interesting things? So I built this robot arm that has 3 bending sections and an end effector at the gripper at the end effector, and we did the same process where we collected data, learned the dynamics, and then did control with it. And it was still able to do some trajectory following with the end effector. But when we changed the payload, the performance varied a lot. So shown here are 3 different trajectories all superimposed, where there's a different payload at the end effector. And this plot shows the path of the end effector. it's trying to follow the gray reference trajectory. But as you can see, for different payloads, there's, a lot of overshoot or undershoot depending on the payload at the end effector. And so this isn't really that surprising when we think about it, because we know this is a soft system, there's compliance, and compliance systems deform quite a lot due to loading. But we need some way to explicitly account for the effect of loading in the model. Otherwise, our controller just won't be able to make up for it. And so we can actually do that pretty easily using this data-driven framework. All we need to do is to collect data of the load at the end effector. So we're calling that W here. And then lift that so that we have that explicitly baked into our basis function. And then when we learn a linear representation, we have a model that takes into account the effect of loading on the dynamics of the system. So we did that by collecting more data, but this time over a broad range of payloads. And then we again built up a controller. But so now we have on the left side the video I showed before. On the right, it's this new controller that explicitly accounts for loading and in the model. And what we see is that over the different payloads, the controller on the right is much more consistent. We get much better convergence around the reference trajectory. So that was nice, but it actually only solved half the problem, because this controller assumes that the payload is known at the end effector. And in practice, for most tasks, the payload will be unknown. So here's another point where the linearity of our model is helpful, because now we need some way of estimating the payload online. And we can do that by incorporating a linear observer into the feedback loop. So we put this observer that infers the most likely load based on observations and dynamics of the system. And we get in real time, as the robot moves around, convergence toward the actual payload at the end effector. So the dotted line's the real end effect, the real payload, and the solid line shows the what the robot thinks the payload is. And so now that we, once we had this, loaded model plus this way of doing online observation, we could finally use a soft robot to do the type of pick and place task that could get close to being useful for real world applications. So what we did is we give the robot an object of unknown mass, and then it moves that object around while updating its estimate for the payload or the mass of that object. And then based on its estimate, it moves and drops that object in one of the cups corresponding to that payload. And so for a set of 10 random objects in the lab, it was successfully able to sort all of them by their mass. And in order to do this successfully, the robot needed to estimate the payload to within 50 grams of the real mass, as well as control the end effector position to within 4 centimeter range, which is the radius of this cup. And so, at the time that we did this, as far as I know, this was the first time showing a fully soft robot arm doing this type of, autonomous pick and place type of task. So the techniques for modeling and control that we applied actually, enabled new behaviors that weren't possible. So to summarize, today I mainly talked about the Koopman operator modeling and control code for soft robots. But in other of my past work, I've worked on design-oriented modeling approaches, as well as what we just saw, control-oriented modeling approaches. And both of these are used to demonstrate model-based control of real soft robotic systems. And so taken all together, I think these contributions constitute the beginnings of a framework for soft robot modeling, design, and control that will, eventually lead to much more capable soft robots. And so we're not quite at the point where we can do the type of, elderly assistance and exploration things that I mentioned at the beginning of the talk, but I think this is, a step toward that. So that brings me to the end of my talk. I want to make sure I thank all of the many people that I've collaborated with on this work, as well as the funding agencies that made it possible. And with that, I'd like to thank everyone for your time, and I'm happy to take any more questions that you have.
And then thanks so much.
Thank you. My timing's okay, right? Okay.
Perfectly okay.
It's perfect. Yeah.
Great.
Yes, thanks, Dan, for the great talk. And any questions from our audience?
Yeah, I have a bunch of questions. So it's a super exciting talk, although, as you know, I'm not working in soft robotics, but some of Sysid problems are very similar in other areas. One question, maybe first on the motivation side. There are also other types of high-dimensional embeddings. Is the main motivation of using Koopman in comparison to this type because simply the fact that it makes your system model linear? Like, is this like why people tend to use it in robotics, or are there also other reasons to use it over?
Yeah, I mean that was the main motivation for us in using it is getting a linear representation of the dynamics. And of course, like it's all speaking to your question before, it's all still an approximation. And so there are some things that you can prove, like convergence to the true dynamics as you increase the number of basis functions and things, but those actually only show that for the non-controlled systems case. So whenever we introduce this control input, we're doing a little bit of like crossing our fingers and hoping that it works out great. And so, but that is the main motivation. It's just trying to leverage that trade-off between increasing the dimension but getting something that's linear out of it that we can use for control. It's all about getting it into a format that's better for control.
Yeah, makes sense.
Yeah.
Maybe one more question about the basis functions and the choice of the basis functions.
Yeah.
Do you have for what you want to do for controls a limitation on how to choose these basis functions? So, for example, you chose monomials. Would it be equally easy possible to choose for basis functions some neural network and train jointly basically jointly learn the basis function and the Koopman matrix, which would maybe allow you to model more precise dynamics than just a few monomials will do? Is this something that people will do, or is there some constraint not allowing it?
Yeah, no, it's a great question. No, it's actually, you can really choose the basis functions pretty much arbitrarily. You're choosing a set of nonlinear functions arbitrarily, and so you still get the linearity even if you choose really weird, basis functions. And so that process that you described of training, doing some sort of like joint training to find the best set of basis functions while finding the Koopman operator that corresponds to those is actually, it's been done by a few groups. I mean, a big paper out of Washington. I think the first author was Bethany Lush, Steve Brutton, and Nathan Kutz. They did a paper on that using neural nets to find good basis functions. I think Ryan Robert Cashman's group, Robert, his group has
Yeah.
done some work in trying to find like the right basis functions and do it in a way that you can say something about the convergence. So the choice of basis functions is a very active, research topic, and there are people approaching it in different ways to try to find the best choice, because it all hinges on that. As soon as you limit yourself to a finite dimensional representation, the choice of basis functions matters a lot. And you'll get very different results depending on what you choose and how good they can be at representing the actual dynamics of the system. So you have good instincts. Yeah, you came up with the exact solution that others have done.
Okay, one last question. Yeah, it's kind of an interesting topic, and it's, I think, for me, like the second time or so I hear about Koopman operators. They didn't make it as much yet into mobile robotics, although they are coming. But what you recommend as a good introductory resource to people who would want to get into that topic from a robotics viewpoint, maybe?
Another great question. I think Steve Brunton's YouTube channel, he has some really nice introductory videos on the topic, really in all sorts of data-driven techniques, but especially Koopman operator. I spent, when I was first learning about this stuff, I spent time reading a bunch of more dense papers, and then master student that I was working with found those YouTube videos. And I saw them, I'm like, oh my God, this would have been so much easier to start from where I started. But yeah, Steve Brunton's channel has really nice videos on it.
Okay, yeah, thanks again. It's been a super cool talk.
Well, thank you for having me.
I have a question on the control side of things.
Yeah.
You said that the model you end up in with the Koopman operator is linear but not exact. Are you able to give like guarantees for accuracy and also stability of the MPC control in the end, or do you model this inaccuracy somehow in the controller?
Yeah, so I don't, in this work, I don't have any formal guarantees of the accuracy of the model. It's pretty much train and see what comes out of it. If you have, and part of the reason is that because like I don't have even the nonlinear, I don't even know the nonlinear dynamical equations for this system. I know nothing, and so I'm just building it from data, and then seeing what I get. But if if you start from a nonlinear description of your dynamics and you actually have access to those equations, there are some things you can do to put a bound on sort of the approximation error in the Koopman linearization. And so that, some of that is from what I was mentioning. There's work on using polynomial basis functions and then using sort of Taylor series theorems to bound that error. But it's not something I did in this work.
Okay. Thanks.
Yeah, I have a lot of questions.
Sure.
Yeah, hi, I have a question. So the Koopman operator looks to me a bit like the kernel method in machine learning, like regression or classification. So can you comment on like how do we compare kernel method and the Koopman operator? And specifically, is there any kernel trick we can use for Koopman operator in this field? Like we compute the kernel matrix instead of the explicit forward matrix. Which is the key here. Is there such case?
Yeah, that's a great question. Yeah, so it's very similar to, it really is the same idea as kernel methods, where you have a late in a latent space, you have a representation that, you know, is nicer than your in the regular state space. But you bring up a good point. You know, in kernel methods, we have the kernel trick, which basically lets us, instead of having to explicitly lift into the infinite dimensional latent space, we know the inner product.
Yes.
And you know, in this work, we actually are explicitly lifting up into the higher dimensional space, and we have to use this finite dimensional restriction because we don't have that same, you know, kernel trick where we can sort of stay in the space that we like, but get the benefits of that latent space representation. As far as I know, that is a sort of a limitation, and we don't have the equivalent of a kernel trick. It's something I've spent some time thinking about. I think some others have spent some time thinking about, and so, you know, maybe someone will come up with a way of you know, giving some sort of benefit similar to that trick. But as far as I know, to do this with dynamical systems, we still have to lift into the higher dimensional space and actually do the computation up there.
Yeah, I see. Yeah, kind of like just technical formulation seems like in regression we are learning like we are doing k input, one output, but here we are learning a four dynamics, so it's like k input, k output. So it's like at least the computation there should be like k-fold. Yeah, it seems like not so straightforward.
Yeah, right. Yeah, we're not losing, we're maintaining the dimension across times.
Yeah. Yeah, thank you. Very interesting.
Thanks.
So since we have mentioned kernel methods in machine learning, well, is there any papers in your field that have leveraged, you know, neural network, or I mean more complex nonlinear formulation to approximate such dynamics, or if they are not doable because of the, I don't know, like lack of data or some sample inefficiency in robotics? Do you have anything to comment on?
Yeah, you just mean in soft robotics?
Right.
Is there, yeah. Yeah, there's actually, there's a lot of groups using neural nets to model soft robots at all sorts of levels of abstraction. So some, it's, you know, just modeling sensor networks and getting their output through neural networks, and others it's explicitly modeling, you know, the dynamics from at a high level, so like the full end-to-end learning type stuff. And there's also more recently work in using, you know, higher fidelity simulation plus reinforcement learning to just learn, you know, policies, using things like domain randomization to build policies that are robust to the modeling error that you have in that sim to real gap. So I'd say in soft robotics, I mean, we're using every tool, like any hammer that we can apply to the nail is being used, because it's a tough problem in how do you actually predict how these things will behave and then, you know, control them. So.
Right. So, but those neural network based methods doesn't show you know, very clear advance over the maybe kernel or traditional methods, because in some other fields I know people use neural network or they use reinforcement learning, and it's, I would say, much stronger than some traditional algorithms. So people just go for neural networks. And
yeah.
But here, are there any issues that or any intrinsic properties of soft robots that prevents people from just all in neural network? And yeah.
Sure. Yeah. I mean, that's a good question. So I mean, one of the reasons that I talked about a little bit in this talk is you can get good predictions from neural networks for the behavior of soft robots. It's just that representation isn't necessarily the most amenable to efficient control, which is why this Koopman approach is useful. But one thing about soft robots that there's no way to get around, whether you're using Koopman operator or physics-based models or neural networks, is if you really want to model everything about the system, it's super high dimensional, right? Because deformation it's an infinite dimensional kinematic system if you want to get like the continuum shape of these things. So even if you're training neural network models, you either have to restrict it to looking at just the output of the end effector position, or have some represent the shape as like a low dimensional polynomial or something. Like you have to deal with the infinite dimensionality of the the shape of the system in some way.
That's right.
So I'd say that is something that's a challenge no matter what approach you're taking to modeling them. And one that I actually think like that's where it's sort of, in my mind, the connection between like design and control comes in. Like there are some things that you can do in the design of your system that still give you a lot of the things you like. You can build something that's highly compliant and has an ability to adapt to a wide range of shapes, but you can make it so it's closer to like a hyper redundant, like you can localize deformations more or less at joints, rather than having something completely continuous. So I think that's a future direction of the field, is like figuring out what the right distinction is to model your system, and then also change your system to make it more amenable to modeling and control, and thinking of all three simultaneously, because you kind of have to.
Yeah, that's pretty cool. Yeah, thanks.
Great. Any other questions?
Yeah.
Yeah, if no other questions, maybe it's a good time to end here. Yeah, thanks Dan for the great talk, and thanks everyone for attending.